Hi everyone, welcome back to another Excel Academy YouTube video. Today we're going to be looking at the recovery of aluminium from bauxite, which forms part of the chemistry section under the IEB Physical Sciences syllabus. So what do you have to learn according to the SAGs, or what do you have to know by the end of this presentation? Now, before we begin, I want you to please take note of this. The information within this presentation is correct as of December 2021 and as per the 2021 Physical Sciences Subject Assessment Guidelines. And the information within the subject assessment guidelines is subject to change. And as a result, the information within this presentation may also change, right? So please, I urge you to check the SAGs regularly. Please consult with your teachers to find out, what has been added, what has been removed, because often the SAGs is updated annually and it's updated quite regularly. So please check with your teachers what has been added or removed from the SAGs document so that you stay on top of things, right? So in this presentation today, we're going to be taking a look at the recovery of aluminium from bauxite. And the subject assessment guideline states that when given a diagram of a cell or other relevant information, you must be able to predict and explain the features of the following electrolytic processes. Now, as I said, we're going to be looking at the recovery of aluminium from bauxite. And that includes the use of cryolite and its effect on the cost of running the cell, the corrosion of the graphite anodes, and the potential risks to the environment posed by using the cell. So keep this as a sort of checklist, and by the end of this presentation, you should be able to tick all three of these bullet points because you should know how to answer questions on these three bullet points, and you should be able to understand the mechanics and the construction of the cell and why, and it's be able to explain and predict why we do certain things in the cell. Okay, now some advice before we begin. Please remember to look at past papers. Past papers are key to success. So I think the Hall-Héroult process appeared in the IEB paper 2 of 2016 and the IEB paper 2 of 2018. So if you do want to see how the questions are laid out and what you are going to expect, sometimes the examiner does change it up a bit, but the content doesn't change much. So if you want to look at the way in which the questions are asked, I suggest you do those two papers and to get a feel of how they're asked and what you are going to expect in the final paper. So why do we choose aluminium? Why? So aluminium is non-corrosive, it's malleable, it's ductile, it's tensile, it's lightweight and strong, it's a good conductor of electricity, it's used in a lot of utensils, and it also protects itself from corrosion by producing a layer of aluminium oxide on its surface, which is very tough. And you can look at the IEB paper 2 2018 memo for a little bit more depth to, or rather the IEB paper 2 2018 question paper to see what I mean, because this sentence or this extract is taken from IEB paper 2 2018. So there are three processes that are involved in the Hall-Héroult process. So the first step is purification. The second step is melting the alumina. And the third step is electrolysis. So let's take a look at the first step, and that is purification. Now, bauxite is about 60% of aluminium 3 oxide, with the remainder being iron oxide and silicon oxide. So we can see that bauxite has a few impurities, and it's treated with sodium hydroxide, and its formula is here alongside NaOH, to produce pure alumina. Now, pure alumina, its formula is Al2O3. Now, the waste from treating your bauxite to produce pure alumina is an alkaline suspension of iron 3 oxide, and it's dumped into red mud dams, which is pictured here. Now let's look at the second step, and that is melting the alumina. Now, as we spoke about, alumina, its formula is Al2O3, and it's insoluble in water and therefore has to be heated into a molten liquid. Now, the reason why it has to be heated into a molten liquid is because it's an ionic substance, right? And we know that ionic substances, they can only conduct electricity when dissolved in an aqueous solution and when it's molten, or when it's a molten liquid, because of the free ions in solution, or the mobile ions in solution, being able to conduct electricity. Now, we already said here that alumina is insoluble in water, so therefore it has to be heated into a molten liquid. You get what I mean, right? So it has to be heated into a molten liquid so that it can conduct electricity due to the free ions, or due to the presence of free mobile ions in the liquid, right? Alumina is then dissolved in molten cryolite to lower the working temperature to around, I would say, 950 degrees Celsius, and thus provides a saving on energy costs, as less energy is used to melt the electrolyte. Now, let's take a look at the inner workings of the cell and the construction of the cell. So we can see here that we have a steel cell, an outer steel cell, all right, and we have our graphite anodes and a graphite cathode, and we can see that our cathode is basically the lining of the cell. So what lines the cell is graphite, and that forms your cathode. We can see here that your bauxite ore, is dissolved in molten cryolite, as we said, to lower the working temperature, right, to about 950 degrees Celsius. And electrolysis results in molten aluminium forming at the bottom of the cell, all right, and your molten aluminium is siphoned out from the cell or from an outlet tube, or it's siphoned out of a siphon or an outlet tube. All right. Now, it's very important that you take note of the oxidation half reaction, the reduction half reaction. Remember that oxidation occurs at the anode and reduction occurs at the cathode. Your net overall reaction is also important to take note of this, all right? And it's also important to take note of how the net overall reaction can also be written. So some additional things to take note of. Now, due to the anode being made of graphite, it will corrode away. Now, it will corrode away because, and it also must be replaced regularly because of this reaction here. So carbon reacts with oxygen gas to produce carbon dioxide. Now, what happens is that oxygen gas is produced at the anode, So oxygen gas is produced at the anode. We can see here the bubbles are depicted here. So oxygen gas is produced at the anode and it reacts with the carbon electrode. So we know that graphite is carbon, right? The oxygen gas reacts with the carbon electrode to produce carbon dioxide gas. And this causes the electrode to corrode. And we can also say that the carbon anode is continually oxidized, right, due to this reaction here. Your graphite anode is used because, firstly, it's a good conductor of electricity. It has a high melting point, and thus it will not melt at the temperature used to keep the electrolyte molten. It's easily replaceable, and it's also very cost effective, which adds to the fact that it's easily replaceable, right? It's not very costly. A large current is needed to keep the electrolyte molten, and large amounts of electricity are needed because the reaction is endothermic. The use of cryolite to decrease the melting point of the electrolyte produces perfluorocarbons or PFCs, which are greenhouse gases. And we know that greenhouse gases are detrimental to the environment because they lead to global warming and, as a result, climate change. Now, some environmental issues associated with this process. Your fluoride emissions are produced, which is what we spoke about on this previous slide here, that the use of cryolite produces perfluorocarbons, PFCs, and they are greenhouse gases, which are very detrimental to the environment, right? Your alkali from the red mud dams seep or can seep through the soil and contaminate water supplies, right? A lot of energy and electricity is required to keep the electrolyte molten, which leads to a lot of pollution being created due to the usage of fossil fuels. It can also cause damage and destruction to habitats and environments, which can leave a scar on the landscape, right? And mining cryolite damages the environment. Thank you so much for watching. I really do hope that you found this presentation helpful. If you did, please remember to like and share this video, and remember to subscribe to the channel for more content to come.